So it's been now 4 or 5 years that I'm working on the question that I will talk to you about today. So I hope to share with you my motivation, enthusiasm, sometimes frustration, because you will see that there are several remaining open questions, and hopefully foster some interesting discussion. And of course, I cannot. Yes, okay. So this is the outline of my talk. I will introduce the question I want to raise, which is about pointwise dissipation in time delay system. I will show you some results for input-free systems, show you that the question that I'm raising is solved for the integral ISS property, but not yet for the ISS property, but anyway, we'll give you some particular classes of systems under which the problem is solved. And the conclusion will present some perspective and suggest some ideas for future work. So let me start with the background. So what is a time delay system? What are ISS and integral ISS in this context? And what characterization we have? And I will also introduce an example that I will use throughout the talk to illustrate the results I will present and introduce the main question. So I'm considering here time delay systems. So the state is xt, which is a segment of the solution over a time horizon of length theta, theta denoting the maximum delay that is involved in the system. So this segment belongs to a set x, capital X, which is a set of all continuous functions from minus theta to 0 to Rn. And so xt of tau at a given time tau is just defined as xt plus tau. The input, as classical in ISS theory, is assumed to be measurable and essentially bounded, taking values in Rm. And the vector field, well, it's just assumed to be Lipschitz unbounded set and to satisfy to be 0 at 0. Okay, so in order to solve such a dynamical system, you need to be given an input signal u and an initial constant, which is a whole segment of initial states, and then you have x of t, which is the current value at time t, and xt, which represents the previous segment, history function, we call it. So I will use two norms when I talk about a point in Rn, so like x of t, I will use a Euclidean norm. And for a signal, I will use the norm with double bar, defined as the sup over the interval of definition e of this signal. Sorry, it's a y of t here. So for instance, xt is defined as the supremum over this, this time interval, so it will be this value here. So ISS, I'm sure that now people get to, to know this concept, but in a time delay context, this is defined like this, very similar to notions we have seen in previous seminars. So the solutions norm has to be bounded by a decaying term of the initial state, the KL function here, plus a k infinity term of the input magnitude. So the only difference with the finite dimensional case is the fact that the initial state is no longer a point in Rn, but a segment. So it's really a straightforward extension of the ISS according to Sontag. And it's been studied quite a while now in a time delay context. I give you a list of example references dealing with this aspect. So what is cool about ISS that not only it provides zero gas, meaning that the system without input is globally asymptotically stable, but also some robustness properties. For instance, we see straightforward from here that whenever the input u is bounded, well, the solution is bounded too. And we can also check that when the input vanishes tending to 0, this ensures that the solution itself will tend to the origin. And we have also this asymptotic gain property, meaning that the steady state behavior of the solutions norm is upper bounded by a k infinity function of the input magnitude. So it has proved useful in several different contexts, and here I want to study it in a time delay context. So a relaxation of ISS is integral ISS. It's slightly the same spirit. The main difference is that the solution now no longer takes into account the input magnitude, but rather its energy. You see that this integral term can be seen as the measure of the energy fed to the system by the input. That's the main difference. And it appears to be a weaker notion, at least in a finite dimensional context and also for time delay system. So it's really straightforward extension also of the integral ISS notion of Sontag, studied in those papers in a time delay context. And here also, there are some nice properties. Beyond zero gas, we have the bounded energy converging state, meaning that if this term from 0 to infinity is finite, then not only the solution is bounded, but it actually also tends to the origin. So there are ways to establish iISS in an integral iISS in practice, and the characterization that was obtained by, so for the sufficiency part by Pepe et Zhang in 2006, and for the converse part in these two other papers, Karafidis 2008 and Lin and Wang 2018. It tells us that if we find a functional called Lyapunov-Krasovskii functional, we sometimes call it LKF, which is lower bounded by the Euclidean norm of the present value of the solution and upper bounded by the supremum norm of the history. So this is the different norm is a novelty with respect to the finite dimensional system, but most of the Lyapunov functionals that we use, they are not say coercive, so it's not possible often to get a strict bound like this involving the whole history function on the left. So we have such a functional, and we require that its derivative along the solution of the system be upper bounded by a negative term involving the whole Lyapunov functional itself, plus a term involving the input. Okay, so very much like the finite dimensional case. Difference is that this derivative here that I wrote v dot for short is defined as the Dini derivative, upper right Dini derivative along solution. And in some papers also, we can reformulate all these concepts through driver's derivative, which owns the advantage of putting conditions without requiring even formally to write the solution. You see here, theoretically, you would need the solution to express these bounds, but of course, this all can be checked without knowing the solution a priori. That's the whole point. So what is important to keep in mind is that the upper and lower bound on the Lyapunov functional, they differ, they are not the same. And most importantly, in this characterization, so I insist it's a characterization, it's an if and only if. So the difference between iISS and integral iISS is that for iISS, this dissipation term here is required to be k infinity, so to be unbounded, whereas for integral iISS, it's just required to be a positive definite function. So in particular, I can tend to 0 as this argument tends to infinity. But in both characterization, what is important is that the dissipation rate here involves the whole Lyapunov functional itself. Okay, this is key for what I will present today. So let me introduce an example. So actually, to give you some context, this is how I started to get interested into time delay systems, because I apply some control theory tools to neuroscience, and a typical model in neuroscience to model the activity of a neuronal population is through what is called the Wilson and Cowan model. So here I made it simple. There is just one population. I don't take into account synaptic weights, but essentially the activity tends to decrease due to this exponential decay up to what is fed by an external input, like other neurons, for instance. And these delay terms, which represent the fact that the communication between neurons is not instantaneous, but the information has to travel across the axon of the neurons. And the function S is typically a sigmoid function or a saturation, something like this. But anyway, here we assume that its derivative is everywhere below 1. Okay. So if I am to study such a system, my natural choice would go for a quadratic Lyapunov-Krasovskii functional, meaning a quadratic term in the present value of the state plus an integral term of a quadratic function of past values of the state. So this is indeed a candidate Lyapunov functional because I can lower and upper bound it, as I showed you previously, and you see that necessarily here the lower bound you get is in terms of the current value of the state norm, not xt, and the upper bound on the other hand can be xt. Okay. And if I compute the derivative of this, so how do I do this? This is just the derivative of this term will just be x of t times the vector field that is here. So that's this whole term here. And then I need to differentiate this, and this is differentiating an integral. So it's just the value of x at time t squared minus x at t minus theta squared. So I get this. When I use the fact that the Lipschitz constant, let's say, I mean, the maximum slope of my function s is 1, I can easily show that v dot is smaller than minus x of t squared plus u of t squared. Okay, you can actually get also some delayed values like some epsilon x of t minus theta, but they will not serve our purpose today. But the point is that all the terms that appear here, among all the negative terms that appear in this expression, there is no integral term here, as here. So there is no hope to get a Lyapunov-wise dissipation, meaning a term like alpha of v. All you can get is alpha of x of t, okay? And this, I call it a point-wise dissipation because it's a dissipation that takes place only involving the current value of the solution and not the whole state or the whole Lyapunov functional. So I'm not saying with this example that the nice characterization of iISS that I showed before is useless. Huh? There are a lot of tricks existing in literature to get such a Lyapunov-wise dissipation, and a common trick is to add an exponential in the kernel of this integral rather than just having one here. We add an exponential term like this, and just by magic, this appears some minus v in the derivative, which fits the criterion I showed you before. But in my opinion, these kind of tricks, they are mathematically interesting, but they have, first, they are ad hoc. They depend on the application you have in mind. You need to make such a modification depending on the system you're considering. And also, I don't think it has a lot of physical meaning. It's more an artificial trick to try to fit to an existing result. So the question I want to solve today, I mean, I will present you partially some results, but I would once again welcome any suggestion you might have for the open problems that are remaining. So is what stability and robustness properties can be derived if we only have a pointwise dissipation rate? So once again, meaning that the Lyapunov functional dissipates only in terms of x of t, not in terms of xt or in terms of the whole Lyapunov functional itself. So I will first talk about input-free systems. So just to make it clear, what I will call now an LKF, Lyapunov-Krasovskii functional, is any Lipschitz unbounded set function, lower bounded by a function of the current value of the state, and upper bounded by the supremum norm of the state. So here I took a generic segment phi, but what you should have in mind is that this is x of t and this is xt. And I will call it coercive if the lower bound is replaced by a function of the whole supremum norm of the history of the function. Okay, so much harder once again to get in practice. So the characterization we have for global asymptotic stability is not my result. It goes back to the work of Krasovskii and also more recently by Pepe and Karafilis, is that the following statements are equivalent. The fact that the origin is globally asymptotically stable is the same as requiring an LKF which dissipates pointwisely, or dissipates history-wisely, or dissipates LKF-wisely, meaning involving the Lyapunov functional itself. So when there is no input and when you deal with asymptotic stability, you don't care so much. There is not much difference between dissipating in terms only of the current state value or dissipating in terms of the whole history function or the Lyapunov functional itself. So that's good news. But as soon as, okay, so actually this requirement, so the weakest requirement we have here is probably this one, because this dissipates only in terms of the current value of the state norm. And in this proposition that is in a recent paper that is hopefully to appear soon, we show that this requirement can actually be relaxed, and that global asymptotic stability is actually equivalent to having a KL dissipation rate. What I mean by KL dissipation rate, it means that it dissipates increasingly in terms of x of t and potentially decreasingly in terms of the history function. So I'm not saying it's revolutionizing the analysis of time delay system, but it's just weaker than the pointwise dissipation. And we will see that it's, for instance, useful when you deal with Lyapunov functional that takes the form logarithm of 1 plus w, where w is another Lyapunov functional. Okay, because this, when you differentiate this, you make appear at the denominator 1 plus w itself, and so you have a decaying term in w, so also in the history norm. Okay, so keep in mind that a KL dissipation rate is also enough to establish global asymptotic stability. For global exponential stability, now I require that my alpha bounds on V are no longer whatever k infinity function, but quadratic function like this. So k of x of t on the right, k of x of t squared on the left, sorry, and k bar of xt squared on the right. And surprisingly, we couldn't find in the literature the fact that having such a pointwise dissipation for global exponential stability is enough to show global exponential stability. So the only result we have so far in that direction is this one. Under the condition that f is globally Lipschitz, which is, I think, a hard requirement, but it's all we have so far, then it's equivalent to request global exponential stability, or to request a history-wise quadratic dissipation, or a Lyapunov-wise dissipation, linear, or a point-wise quadratic dissipation. Okay, so this is, I think, rather intuitive. It corresponds a lot to the finite dimensional case, but we were able to prove it only when f is globally Lipschitz. Okay, so the idea of the proof is you start with LKF, which is thus pointwisely dissipating, so you call it V, and you modify it by adding epsilon times another functional W. And this functional W is defined like this, the integral, so it's a bit tricky. Integral from t minus theta, so theta is the maximum delay in your dynamics, of the max of the square of the norm of the solution, okay? What is important to notice is that the variable of integration here is tau, and tau has only an influence on the length of the interval on which you compute this max. Okay, so why this choice? Because if you differentiate just this W functional, you have to differentiate an integral. So you first have to take this quantity at time t, and this is the max from t to t of x of t, so it's just x of t squared. Then you have to take minus the value of this function at t minus theta, and you get the max over t minus theta to t of x of s, which is nothing else than the history function. And then you have to take the integral of the derivative of what's inside the integral. Okay, and this is a mess, but we managed to show that it's upper bounded by 2 times the maximum delay times the state times the vector field. That not much we can do more. So then the idea is to use the fact that f, this is where f needs to be globally Lipschitz, in order to be able to compensate this bad term through the good terms that we have here. So the key point is that you see that with this trick, we make appear a history-wise dissipation. We have minus the history squared, okay? This term here, we will compensate it by the fact that V is pointwise dissipating, and these two terms, using the Lipschitzianity of we will be able to compensate it for epsilon small. And that's how we got history-wise dissipation, from which it is easy to show global exponential stability. Okay. So going back to the Wilson and Cowan example, so this is the dynamics. When there is no input, you don't have the U term here, you just have this. Easy to check that the system, the vector field is globally Lipschitz with Lipschitz constant 3 because S has Lipschitz constant 1. The Lyapunov function I presented you before is this one. We have already seen that it's bounded like this, so it's indeed a candidate for global exponential stability with k underline equal 1, k bar equals 1 plus theta. And when you compute the derivative, that's what we've done before, we'd get, according to the previous theorem, that k equals 1. So all the assumptions are fulfilled, and you get global exponential stability of this system without requiring anything else than a pointwise dissipation once again. Okay. So the open question remaining in this, in the context of input-free system, is this one. Can, under the same condition as before, so meaning with a point-wide quadratic dissipation, is it enough to get global exponential stability even if f is not globally Lipschitz? So this, to my knowledge, is an open question. It sounds quite reasonable to say that the answer is yes, but I have no proof of this. All I can say is that this paper by Di Fernando, Pepe, and another co-author, who I forget, sorry, who's showing that under this condition, not only you get local exponential stability, but also global asymptotic stability, but still it's far from being global exponential stability. Okay, so that's the first open question that I'd be happy to discuss with you if you want. Let me now go to systems with input and study integral input to state stability. So you remember you bound the solution by the integral of the input. So for this, I first need some tools. And the first tools I need is the characterization of zero gas. And I recall that zero gas means that the origin of the input-free system, you see that U equals 0 here, is globally asymptotically stable. So there is a result by David Angeli and co-authors in 2000 in a finite dimensional context that is simply extended to time delay systems here. It says that the fact of being zero gas is equivalent to having a coercive Lyapunov-Krasovskii functional V. So it's important to notice that this is a strong generation of a Lyapunov functional because it generates a coercive one, such that you get a negative term that involves the whole history function. So very strong dissipation rate here. But the price you pay, of course, is having an unknown term here involving also the history function. And potentially this L can be very big, so you cannot derive much from this expression. And indeed, you only have zero gas, so there's not much robustness you could hope for. So this is the first characterization of zero gas. And the other one is to say that paying the price of composing V with a class K function pi, so I insist it's a class K, not K infinity, it might be bounded, this pi. So if you compose V with, it's not the same V, or maybe it's the same. If you compose V with this K function pi, you get a Lyapunov. It's not a Lyapunov functional because it's not radially unbounded, but it looks like it. It's not proper, but its derivative now looks very familiar. Negative term in the history function plus positive term in U. So of course, if pi was K infinity, then we expect this to show integral ISS, and we know that zero gas in general does not imply integral ISS. So the fact that pi is allowed to be a class K function only is important. So this is just a delay extension of Angeli and all. I'm not saying that the proof is straightforward because of the coercivity requirements and the fact that you have additional terms coming into play here. But it's really the same spirit. Okay, the second tools I need is some solutions-based characterization of integral ISS. And for this, I need to introduce the notion of UBEPS, meaning uniform bounded energy implies bounded state. So it's just saying that up to a K infinity function of the up to a K infinity function, the solution is bounded by a function of the initial state plus the integral of a function of the input plus possibly a constant C. So in particular, you see here that whenever the energy fed to the system, I mean, this energy term is finite, then directly the state is finite. So that's why we gave this name. And the second solution I need, the second notion I need is zero output dissipativity. So it requires that there exists a LKF-V such that V dot is smaller than gamma U of t. So it's a rather weak assumption. You have no negativity in terms of the state here, but just involving the input, a positive term in the input. And we call it coercively zero output dissipativity simply if V is coercive. Okay, so here again, these are natural delay extensions of the work by Angeli and co-authors. So based on this, I have this characterization of integral ISS. Integral ISS is equivalent to requiring zero gas, so global asymptotic stability in the absence of an input, plus either coercive zero output dissipativity or simply zero output dissipativity, or UBEPS with C equals 0. You remember there was a constant C here, so you might even require that the UBEPS property holds with C equals 0. And combined with zero gas, all these notions are equivalent to integral ISS, which is not very surprising in view of the results for infinite dimension provided by Angeli and co-authors. And I want to mention that the crucial step of showing that integral ISS implies coercive zero output dissipativity, so this is essentially a converse result, comes from a result by Lin and Wang in 2018. Okay, so now that I have this solutions-based characterization and a characterization of zero gas, I can present the main result of this section, which is several characterization of integral ISS. And here I show that integral ISS is equivalent to history-wise dissipation with a coercive Lyapunov function, simply history-wise dissipation, or Lyapunov-wise dissipation, or even KL dissipation. Okay, so this is probably the weakest requirement you can get. Once again, it's increasing in x of t, but decreasing in the history norm. Okay, and what we can show also is that if you have a pointwise dissipation, because that was the main question of today, a pointwise dissipation like this, minus alpha of x of t, where alpha is just a positive definite function, implies indeed integral ISS. So this solves the main question as far as integral ISS is concerned. And the proof structure is this one. So we going from a coercive history-wise, of course, you get a history-wise, this is trivial. But from history-wise to LKF-wise, and from LKF-wise to a KL dissipation, from point-wise to KL dissipation, all these black arrows are rather easy to show. It's essentially manipulations of comparison functions and not so complicated. The two difficult parts are the blue arrows. So going from a KL dissipation to integral ISS, and probably that's the main contribution of the theorem I showed you before. So how to show this? We start from a KL dissipation, so it means minus a KL function of x of t xt plus gamma of u. This is what it means by KL dissipation. And from this, you get two information. First, that when u equals 0, you get a KL dissipation. And this I've shown you before that it implies global asymptotic stability. So from this, we have 0 gas. And the second information is that since this term is non-positive, we directly have v dot smaller than gamma of u. This means that the system is 0 output dissipative. And so since we have seen before that 0 gas plus 0 output dissipativity implies integral ISS, you get to this. Okay. And the last remaining term, this blue arrow here, going from integral ISS to coercive history-wise, you start with the fact that integral ISS implies 0 gas, and you use the characterization of 0 gas that I gave you before. So there exists a Lyapunov-Krasovskii functional V1 coercive, but maybe non-proper, maybe not radially unbounded, which satisfies minus alpha xt plus gamma of u, where alpha is a PD function, positive definite function. And by Lin and Wang, using the fact that integrally, they showed there in 2018 that integral ISS implies coercive 0 output dissipativity, meaning V2 dot smaller than gamma of u. So when you add V1 and V2, you get a coercive proper Lyapunov functional, and you can easily show from these two bounds that you get a coercive history-wise dissipation rate due to this term here. And the proof is done. So then I will use this to study a cascade of integral ISS systems. So in cascades, you have an input U that is fed to a first system called the driving subsystem in terms of Z. And this Z serves as an input to a second subsystem called the driven subsystem here. But the driven subsystem has no influence on the driving subsystem. That's why it's a cascade. But maybe U can directly have a feed through on X. Okay. So it's interesting to study cascades because sometimes it appears naturally due to the physical nature of the system. And sometimes you can design a control law that put the system into cascades in order to simplify the analysis of stability. So the whole point in cascade-based control is then to simplify the problem by subdividing the big system into smaller ones that are easier to study. So this has been widely studied in a finite dimensional context, starting from Seibert and Suarez probably in the 90s. And also with delays, much fewer works. I can mention the work of Sedova in 2008, who relies on Razumikin approach to solve this problem. And also Ito and his co-authors who studied this problem through small gain results, because a cascade is nothing else than a feedback when you don't have we have a zero gain somewhere. Okay. But the key point here is that unlike ISS, integral ISS is not preserved by cascade interconnection. And this is true already in finite dimension. Okay. So you need some other conditions. And the other conditions often take the form of growth rate condition. And this is the result I want to present you. So this is the cascade I have, driven subsystem, driving subsystem. And on each of these systems, I assume integral ISS. And more precisely, I assume that I know a first Lyapunov functional V1 associated to the driven system, which has a KL dissipation rate. Notice that here the second argument is Lyapunov functional itself rather than the supremum norm of the history, which is a slightly more requesting than what we have seen so far. Sorry. And then you have positive terms that represent all the inputs to the system. What are the inputs? They are delayed values of the Z subsystem and the exogenous input U. Okay, so this essentially requires integral ISS of the first system. In the same way, this requires integral ISS of the second system, and once again we have a KL dissipation rate in terms of the Z variables. Okay, and so this is not enough to conclude integral ISS of the cascade. But a sufficient condition for it to be integral ISS is to have this growth rate condition that the sigma I, so the dissipation rate of the second subsystem, dominates the input rates of the first system around 0. That's what this lim-inf means, just a domination condition around 0. And what is cool about this result, and was not present even in the finite dimensional context, is the fact that this growth rate condition needs to be checked only for all I in this set I, capital I. What is capital I is the set of all indexes of the z variables that enter the computation of the first Lyapunov functional. So if by some chance z2, for instance, does not appear in this computation, then you don't need to check this growth rate condition for the z2 variable because it will have no critical impact on the stability of the cascade. So, so as I told you, the growth rate restriction is only about the terms that actually appear in V1, not only on the variables. It allows a KL dissipation rate. So in particular, it allows for a pointwise dissipation rate, which I think is useful in practice. And maybe the main drawback of this theorem is the fact that all the terms appearing in Z, so Z seen as the input of this first system, they have to be in terms of discrete delays. It's not possible so far to consider distributed interconnection delays. So you are allowed to have internal distributed delays in this part and that part, but not in the interconnection term ZT. So this is a line of further research. So far we don't have it. So the idea of the proof, I cannot go into details, but you first show forward completeness, then you show zero gas, and for this you consider the cascade without input. And since there is no input, you can easily make a change of supply rate and change the supply rate of the driving system as strong as you want, except at 0. Okay, and so that's why the growth rate condition appears only in 0, because it's necessary for the change of supply rate result we have. And so based on this, you get zero gas, and then you show UBEPs, and we have seen before that zero gas and the UBEPs property are enough to conclude integral ISS. So let me just mention that the result seems to be new also in a finite dimensional context. So here you see there is no delays involved anymore. And the corollary, direct corollary of the previous result is the fact that, so now it's V1 and V2 are functions, no longer functionals. Here I just assume integral ISS. Here I allow a KL dissipation because once again, it can be useful when you deal with Lyapunov functions in terms of logarithm of 1 plus something. So that's why I allow a KL dissipation. And I have a similar growth rate that the dissipation rate of the driving subsystem need to dominate the input rate of the driven subsystem. But once again, only for the terms that actually appear in the computation of V1. You don't care about the other terms. And so you get integral ISS also in a delay independent context. So open questions about integral ISS. I identified 2 of them. If you remember correctly, in my characterization of integral ISS, what I managed to show is that a pointwise dissipation ensures integral ISS, but we are not sure about the converse. All we have so far is KL, history-wise, Lyapunov-wise, but it's not clear at all whether any of this property can ensure a pointwise dissipation. And this is due to the fact that alpha is just here required to be a positive definite function, so it's not monotone, okay? And so you cannot go from xt, which is bigger than x of t, go easily from here to there, because you can really have a very strong decay when xt tends to infinity that's not captured by this term here. So I'm not saying that this is a very a question of strong importance. It's just out of mathematical curiosity. I believe that in terms of sufficiency, this is the most interesting result. And in terms of converse result, most of the time you would like to have either a Lyapunov-wise dissipation or a history-wise dissipation, but it's little likely that you need such a point-wise dissipation. But it's still a question of curiosity. And the second open question is whether, under similar assumptions at the cascade result I showed you, it would be possible to involve, to authorize distributed delays in the interconnection. So you remember, so far, I require that all my interconnection between Z and X is through discrete delays. Not clear to me whether similar results could be obtained through pointwise dissipation to show the cascade is integral ISS in presence of distributed delays in the interconnection. Okay, let me now move to iISS. So iISS, so the conjecture, so that's the conjecture that drives me nuts for 5 years now. I've I've annoyed a lot of people present here today with this question, and so far there is no satisfactory response to this question, neither proved or disproved. So the question is whether, when you have such a pointwise dissipation rate with alpha being class K infinity, whether or not this implies integral iISS. Sorry. So we've just shown that the question is solved for integral iISS, but in the case of iISS, it remains an open question. So the good news is that we know that the converse holds from the results of Karafyllis and co-authors since 2008, but the sufficiency part is not clear at all. What I can say is that in the delay-free case, this question is totally irrelevant because pointwise dissipation is equal to Lyapunov-wise dissipation. It's just because due to the fact that V is upper and lower bounded by K infinity function of X, so you can, from a pointwise dissipation, you can easily get a Lyapunov-wise dissipation. So the problem is irrelevant in a finite dimensional context. So there was an attempt by Kankana Melage and Wang and Lin to show, so sorry for the pronunciation of this name, an attempt to get a pointwise dissipation. So it's using iISS Lyapunov functionals in an implication form. So here indeed you request only, and it's an if and only if, it's characterization of iISS, you require only a pointwise dissipation, but the problem is that you request this dissipation to hold whenever the LKF is greater than chi of u. Okay, so it's indeed a pointwise dissipation rate, I agree, but it needs to be checked. In order to be checked, it needs to involve some terms in V in the derivative of V. For instance, in the example I used before, Wilson and Cowan, we have seen that V dot is smaller than minus xt squared plus u of t squared. And from this expression, I see no way to be able to check such an implication because there is no V term appearing in the derivative. Okay. One context in which I can answer the question of iISS through pointwise dissipation is when the system is globally exponentially stable, when there is zero input, and the vector field F is globally Lipschitz. So this is a slight relaxation of global Lipschitz in terms of the input, but forget about it. Essentially, it requires that F is global Lipschitz. Then directly you have iISS. So this is a result that goes back to Pepe and co-authors. And since guess we have seen that we can establish it in the global Lipschitz case through a pointwise dissipation, this is a way to show iISS through pointwise dissipation. So back to the example, we had this system here. If I consider the input u equals 0, we have seen that v dot is smaller than minus x of t squared. So I indeed get a pointwise Lyapunov-Krasovskii functional for global exponential stability. I can easily check that this inequality is fulfilled with just c equal 1, q equals 0. So I get iISS for this system. So when can we say that a pointwise dissipation is indeed ensures iISS? So there are two ways to do this. Either when restricting the upper bound on the Lyapunov functional or restricting the vector field. So the first result is about restricting the upper bound on the Lyapunov functional. So I assume that the upper bound on V is not whatever k infinity function of the history function, but can be decomposed in a non-delayed terms plus a nonlinear function of integral of the delayed terms. Okay. So what matters is the function alpha 3 in the kernel. So if I call alpha the pointwise dissipation rate, and this alpha 3 is dominated at infinity by this dissipation rate alpha, then I get iISS. Okay, so I think this bound is interesting per se. It covers a lot of Lyapunov functional we use in practice, but still it requests this growth rate condition. So just the proof, under this condition, we can show that alpha composed with alpha 3 minus 1 is convex. Based on convexity, I can use Johnson inequality, and then by modifying the Lyapunov functional, by adding this term, this double integral term here, I managed to show, so sorry, this is not a phi, it's a x of s, sorry. I managed to show that this new Lyapunov functional has Lyapunov-wise dissipation rates, and so I conclude iISS. So as a direct corollary is the case when the Lyapunov functional is quadratic, so quadratic in non-delayed terms plus integral of quadratic function of p, and dissipate in a quadratic manner too, pointwise but quadratic. Then I directly add iISS. So going back to the example, the functional v was like this, so I get p1 and p2 equals to 1. The derivative was like this, so I get q equals 1, gamma of s, a quadratic function, and I conclude iISS for this system. And the second way is to restrict the vector field itself by assuming that the integral of the vector field is bounded by integral over a double time interval of the state plus integral of u. So I think that per se, this condition is rather weak requirement. I mean, most of the vector fields I would have in mind can be decomposed like this. The key condition from here is that this function alpha1 here, appearing here, once again has to be dominated by the dissipation rate alpha around infinity. Otherwise, you might not get iISS. I mean, at least we don't know. So yeah, just very quickly, that's to show you that this worked for the system we have in mind, because the integral of the vector field is like this, and so I get alpha1 equals 3s, and the dissipation rate was s squared. So when I do alpha over alpha1, I get s over 3, and this indeed does not vanish at infinity. So I'm fine, I get iISS. Maybe I will not go through the proof, but yeah, maybe this picture is interesting. What I managed to show, and this is common to whatever pointwise dissipation, is that I managed to show that from times to times, like at an instant t0, t1, the solution enters a neighborhood of the origin whose size is proportional to the input magnitude. So that's the lim property for those who are acquainted with this notion. But it's only pointwisely. I know that there exists a time at which x of t is smaller than this gamma of u, but I have no information on whether the whole history is contained in this ball of radius gamma of u. Okay, so here with the gross rate condition, without going into details, I managed to show that the whole history function works, and that the time between two consecutive such intervals is uniformly bounded. So this is a u-lim property, and I managed to get iISS. So just to conclude the talk, I want to tell you what we have under a pointwise dissipation rate. If we don't have iISS, what do we have? Obviously, we have forward completeness, no finite escape time. Obviously, we have zero gas, and this goes back to the result of Krasovskii. What we also have is a pointwise integral-to-integral property, meaning that if I have a pointwise dissipation rate, then I get that the integral of alpha of x pointwisely, this is very important, is bounded by a function of x0 and the integral of u. So this is by direct integration of the dissipation inequality, and it implies that the bounded energy input implies a bounded energy of the state. And it's a natural extension of the integral-to-integral property introduced by Sontag in '98, and it happens to be equivalent to iISS in a non-delayed context. So a similar result was obtained in this paper by Jacob and co-authors, including Andrei, in 2018. But it requires here, you see that what is in the integrand is no longer x of t, but rather xt itself. And it's not clear at all how to estimate this integral of xt based on some knowledge of x of t. Okay, so we cannot exploit this result, I think. We have also an asymptotic gain, but only in average, meaning that under a pointwise dissipation, you can show that the limit when t goes to infinity of this average of the solution is below gamma of u. So this is again from direct integration. What we would like to get is rather that the lim of x of t is below x of u, because this is a notion of asymptotic gain introduced by Sontag and Wang in 2002, strongly related to iISS. And in this paper by Andrei and Fabian in 2017, the key assumption is the asymptotic gain, indeed, but of the whole history function. And so we are very far from it, because here we have just that in average, we are below at infinity and then gamma of u, but no way to check that the whole history function enters the ball of radius u. The limit property also, but I mentioned this before, I get a pointwise limit property. point limit property is that wherever I start, I will eventually enter a neighborhood of size proportional to the magnitude of u. So this is a contradiction argument, can easily be obtained. We can actually get ulim, meaning that the 2 consecutive times when I enter this ball of radius proportional to u is uniformly bounded. And at this time instant, I can also show that in average, my solution is smaller than some other gamma of u. But still, this doesn't seem to be enough to conclude iISS. So that's a pity, because in finite dimension, we know that lim, this property plus 0 gas, implies iISS. Similar result in a time delay context by Andrei and Fabian in 2017, but requiring that the inf of the whole history signal is below delta of u, which we don't have here. So to conclude, first, I would like to thank my co-authors, Pier Domenico, Johan, Jakub Orlowski, my former PhD student, and my colleagues Yassine, Paolo, and Mario, and also several colleagues with whom I had a very interesting discussion. I hope you're not tired of me asking about this obsessive question. So Fabian, Andrei, Yuan Wang, Yasson, Alexandre Seret, thank you very much for these interesting discussions. And what I presented you today is a relaxed condition for global asymptotic stability, a pointwise condition for global exponential stability, but that works only in the global Lipschitz case. And I gave you a conjecture about iISS that, in my opinion, would simplify the analysis of time delay systems and also unify the theory with respect to the input-free case with the Krasovskii characterization of global asymptotic stability. So I've proved this conjecture in the integral iISS case, but I didn't manage to prove it or disprove it in the iISS case, except for very particular classes of systems. So I would really welcome any ideas and suggestions. And I leave you now with a list of related references. Thank you very much.